All right, so let's continue then. Firstly, thank you for the introduction, which is very good. Now that we can put in context in terms of some of the applications for bioseparations. So as I said, the next lecture we're going to talk about bioreactor harvesting. And if you remember then, that is the first step in terms of trying to recover our product from our bioreactor. Okay, so the aim is that that we are going to use microfiltration with pore sizes from 0.05 to about 10 micron to retain cells and cell debris while allowing proteins to pass through. Okay. I just want to point out that there are some other processes we're going to talk about, all of which are pressure driven processes. So all of these have a driving force that's going to be an applied pressure. So generally it's run in dead end mode for both bioreactor harvesting and also for sterile filtration. And there's also a great deal of interest in using disposable units. I explained earlier this morning that there's interest in using these for one-time use applications. I would also point out that for some of these applications, it's impossible to regenerate in a cost-effective way, and especially when you're looking at removing contaminants in the biotech industry. Just so that you know also, virus filtration, which we'll talk about later, which I told you is kind of between microfiltration and ultrafiltration, uses pore sizes between about 20 and 70 nanometers, also used in dead end mode or normal filtration mode. And again, there are disposable units. Ultrafiltration, on the other hand, is typically used in tangential flow mode and with pore size about 1 to 20 nanometers. So we are going to focus here on microfiltration type processes. So if we think of bioreactor harvesting, as I told you earlier, we are going to run this in a batch process. We are going to look at trying to produce protein-based therapeutics. The word bioreactor harvesting is sometimes replaced by bioreactor clarification. Actually, to be really technically correct, bioreactor harvesting is if you want to harvest the cells, and we don't want to harvest the cells, we want to recover the protein. So typically, technically it should be called bioreactor clarification, but if you look in the literature, people use the word replaceably, but really this is bioreactor clarification. Sometimes you want to grow cells, and then it's bioreactor harvesting. Okay. As I mentioned this morning, cell viability may not be at the maximum. In fact, you want to get to a cell viability that maximizes the amount of product you have. And the aim of this midstream process is to recover product, reject cell debris. Often there is more than one step, and often we have things like centrifugation combined with some sort of depth filtration. Okay. So let's start off first talking about depth filters. So depth filters are going to be dead end normal flow filtration devices. Okay. So dead end normal flow means the same thing. You're flowing perpendicular to the membrane surface. Sterile filtration and virus filtration are also run in normal flow mode. So when you think about those processes I showed you, there are many that are not tangential flow but are normal flow. In the case of normal flow, this is typically one-time use only. You never regenerate normal flow filters. Okay, so depth filters are used once and then typically you throw them away. It is really very difficult to regenerate them. And in fact, you use normal flow when you don't want to regenerate, because tangential flow is just more complicated to run, as we'll see later. Tangential flow filtration is also sometimes called cross-flow filtration, and a recent advance on that is something called alternating tangential flow filtration, which we'll talk about later as well. Ultrafiltration is run in tangential flow mode, and sometimes, I'm going to talk about it also, you have a combined tangential flow and depth filtration. Okay? So all of these are different ways of running these filters. So the next 3 lectures will really focus on bioreactor harvesting, sterile filtration, and the so-called dead-end filtration, which is normal flow filtration and tangential flow filtration. Okay, so normal flow depth filters are used for clarification. They make use of surface interactions, typically membrane surface sieving. It's a batch process, and it's often used in conjunction with another process. So I mentioned there are clarification, often centrifugation. You use centrifugation, but the product from centrifugation often is going to contain some small particulate matter. And the aim is to get rid of all particulate matter. So often depth filters were used as a second operation after something like centrifugation. But today there are standalone depth filters that are used without anything else. So you are using perhaps flocculation precipitation and then the depth filter. Depth filters have a graded pore structure, or you can use, if you like, multiple depth filters in series with different pores to remove a range of cells and cell debris. Okay? So one of the things about depth filters, as the name suggests, is that it's in other sorts of membranes, you are using surface interactions, right? They are rejecting things because of the surface structure. In the depth filter, it's, if you imagine, more three-dimensional. So you actually can remove things through the depth of the whole filter. So if you're working in water treatment, it's like sand filters, right? So sand filters, you absorb stuff all the way through the filter, okay? And as I said here, you have a graded pore structure, so you can start off with pores of different sizes, larger pore size moving to smaller pore sizes. So if you think of the structure of these devices, they are heterogeneous structures consisting of fiber matrix, a filter aid, and binder. So they're fairly complex in the way they are designed. The matrix is a non-woven array of cellulose or polypropylene fibers. The diameter and packing density determine the effective pore size. So these are they're not really cast membranes the way you think of a membrane for filtration. Instead, they contain all these units, and depending upon how you put it together, you come up with an effective pore size. So the smaller debris, protein and DNA, are removed by a high surface area filter aid contained within the matrix. So these are rather complex. They also contain things like diatomaceous earth, activated carbon, perlite, and that is used to absorb some of these contaminants. Now, I mentioned to you earlier that the idea of these bioreactor clarification is to try and remove cell debris, and so forth. But if you remember the scheme I showed you for purification, after that you have various polishing steps and so forth to remove host cell protein, DNA. And I also told you virus clearance is complicated because you need more than one operation. So modern technology has moved towards the idea of, as well as removing cells and cell debris, if we design a filter that has high surface area and can also start to remove some of these contaminants, it reduces the load on subsequent purification operations, right? So that's a big advantage. So that's why some of the more modern depth filters make use of all sorts of things like diatomaceous earth, where you can also show, you can validate removal of host cell proteins, DNA, and actually also viruses. I'll talk about that later. The binder is used to, so I told you there were these various components, right? Filter aid, binder, and so forth. The binder, the purpose is to maintain physical stability of the overall filter structure. But also there is evidence that the binder can be used for adsorptive removal of proteins and DNA. Okay? And then here is a SEM of one of these depth filters that's made by Paul Corporation. So when you think of depth filters, they're actually rather complex. They contain many different components, and besides removing cell and cell debris, you're also trying to see if you can get removal of some of the other contaminants, lowering the load on subsequent purification steps. So these are how depth filters are designed. Now the thing about it is these are small scale depth filters. They look like these little capsules, as you can see here. And as I said, they're one-time use. You use them and you throw them away. Okay? So small scale depth filters are flat sheets in small sealed capsules in the left panel. Pilot and commercial scale depth filters are parallel arrays of these sheets. So you can see here how we can have parallel arrays of the sheets. So as you scale up, I told you scale up is very important in the biotech industry, and you can scale up by just adding more and more and more of these in series, and you can have them in parallel columns, right? So you can just add more and more as you increase your processing volume. But there's one complication, right? So that's great, but you need to do something. You need to have good flow distribution, because if you don't have equal flow distribution between these, then you're having inefficient usage, and you might be overloading one compared to the other. So one can plug and block, and then the whole thing fails. So one of the complications, though, is that you need to be able to have good flow distribution between these parallel paths, right? And this means sometimes scale up and scale down can be difficult. Okay? Now, removal of cells and cell debris occurs on both the external surface as well as within the depth of the filter due to size-based retention by the porous matrix. So as I said, you must consider this as a three-dimensional structure where actually you get removal not just by surface sieving, but by the depth or the material in the filter itself. Steeply graded depth filters, where the pore size decreases by a factor of 10 from the filter inlet to outlet, can provide effective removal of turbidity even in high-density mammalian cell culture streams. So turbidity is another thing that people look at in this sort of in these bioseparations, because the turbidity reduces as you remove more of the small particulate matter. Okay? So that's an important simple way to quantify how well you're removing this particulate matter. And then I give an example here. This particular Clarisol that's made by Millipore provides capacities of more than 100 liters per meter squared. So these numbers may not mean much if you're not working in the area, but typically when you design these units, you're looking at the capacity. You're looking at how much you can remove per surface area of the depth filter. And that's important because I told you these are batch processes, right? So if I have a batch of 10,000 liters, I need to know how much I can remove. Another thing, by the way, about this batch processing is that you like to complete each unit operation in one shift. So it should not take more than about 6 hours because you need time to set up, to clean, and so forth. And in batch processing, the way the biotech industry runs, you don't want to have a change of operators in the middle of a unit operation, because that leads to possibilities of differences between operators and errors and so forth. And remember, this is very expensive, each batch. So the way they like to do it is you run one unit operation, then that shift ends, you move to the next one, then the next one. You can do, of course, two in one shift, but you don't want them going over a shift. That typically determines how much capacity you need. Okay? So 100 liters per meter squared is actually a very high capacity for untreated CHO cell cultures harvested from 80 to 90% viability. I told you cell density is often over 90%, but when you're harvesting, it's less than 90, 80 to 90% viability. And this is typically the cell concentration. So you can see it's 15 to 20 by 10 to the 6 cells per ml. So again, in batch cultures, that's pretty high. Okay? We are also today moving towards continuous biomanufacturing, where people look at something called perfusion cultures, which I'll talk about later. But this is typically what they call fed batch. Okay? Capacity could be increased by more than threefold by treatment with some sort of flocculants, such as chitosan, which flocculates small cell debris and particles. And clarified cell culture fluid can then be processed through 0.2 micron pore size sterilizing grade filter with capacities up to 1,000 liter per meter squared. Remember, in that diagram I showed you, after each unit operation, you typically have a sterilizing grade filter. And that is put as a safety mechanism mainly to make sure there's no possibility of infection. Sterilizing grade filters, as we'll learn later, is the problem there is that they also have a capacity limit, okay? And you don't want to pass their capacity limit, because then, of course, your whole operation plugs. And so 1,000 liter per meter squared is actually a very good capacity for sterilizing grade filters. Recent studies suggest that significant adsorptive removal, this is what I mentioned earlier, of host cell proteins, DNA, endotoxins, and viruses also occurs or can be designed into these depth filters, which will reduce the load on subsequent unit operations. So in fact, today most of the research that focuses on depth filters focuses on designing depth filters that are able to conduct multiple functions. As well as being a depth filter, they are starting to remove some of these contaminants that occur in biomanufacturing. And if you remember that diagram I showed you, you have a capture step and then you have two polishing steps. And I told you sometimes people try to see if they can get away with one polishing step. That may be possible if you can design depth filters that start to remove some of these contaminants. Okay? High ionic capacity depth filters provide 4.8 log removal of porcine parvovirus when operated at low conductivity. It turns out that virus clearance is often very tricky. We'll talk about that more as we talk about virus filtration membranes. Porcine parvovirus is one of the viruses used to validate virus clearance. So I told you there are retroviruses that are produced by cells. So typically you're going to validate retrovirus clearance. You also need to validate adventitious virus infection, okay, contamination. And to do that, regulatory authorities have models. So for retrovirus, there are certain models. A typical one is murine leukemia virus. So it's a cancer virus from mice, but it's a retrovirus. In the case of adventitious virus clearance, the idea is here there could be contamination from animal-derived cell culture media and so forth. So what you want is a worst case. You want to show that if I validate clearance of this virus to certain logs, say 6 log, 10 to the 6-fold clearance, that means I am sure that any other virus that's present would also be cleared because it is easier to remove. Okay? So what makes viruses difficult to remove? Well, the smaller the virus, the more difficult to remove, especially if you are using size-based separations, right? Also, viruses that are more robust, that are more likely to survive in the atmosphere, are more difficult to remove. So retroviruses are so-called enveloped viruses. They have a lipid envelope, and they tend to be more fragile. Okay? So it's another discussion as to why viruses evolve with different sort of envelopes and so forth. But retroviruses tend to be more fragile. So low temperature, low pH hold I showed you earlier, that's good for inactivating retrovirus. Doesn't work very well for parvovirus. Parvovirus do not have a lipid envelope, and they're far more stable. Okay? A good example of a parvovirus is hepatitis B. That is a parvovirus. Okay? And as a human example of some of these animal viruses we're talking about. So the idea is to use a model virus, porcine, which is a type of parvovirus, as well as minute virus of mice, which is a parvovirus that affects mice. Those are two common model viruses. In fact, minute virus of mice is probably more common than porcine parvovirus, but both are used. These two viruses are very small. They're 18 to 20 nanometers in size. So they represent the worst case, okay? Because if you're using size-based exclusion, you want as small as possible. They're also very environmentally stable, okay? So, hepatitis B is quite contagious, right? Because if you don't wash your hands and so forth, people get it. It survives quite well on surfaces and so forth. So that's another reason. So those are the two viruses used. So 4.8 log is actually pretty high for removal of porcine parvovirus. Host cell protein removal by depth filters containing diatomaceous earth or perlite due primarily to electrostatic interaction are positively charged to polymeric binder. So another thing is, if you think of host cell proteins, there's a whole range of host cell proteins, right? Inside a cell, there are many proteins, and their isoelectric point varies significantly. So again, if you're trying to use charge-based separations, you will tend to remove one subpopulation of them, but not all of them, okay? So you get quite good removal by these positively charged polymeric binder. Negatively charged diatomaceous earth provides greater removal of positively charged proteins, obviously. Okay? Hydrophobic interaction provides a significant contribution to binding reactions for some impurities. So there's also this thing called hydrophobic interaction chromatography, right, in bioseparations. So you make use of multiple modes to remove them. And one of the new areas, if you are interested in chemistry and modifying membrane surfaces, is so-called multimodal ligands. So typically we bind quaternary ammonium groups, right, to remove by charge ion exchange. We bind sulfonic groups for ion exchange, for cation exchange, anion exchange, and so forth. But multimodal ligands, where you have, say, tertiary amines or primary amines, are interesting because then you can have charge, but you can also, on the other functionalities, put hydrophobic groups on them. So this is something that's of great interest these days in coming up with these multimodal ligands. Okay? So detailed physical chemistry of depth filters plays a critical role in determining removal rates for small impurities. So I'd say the take-home message is depth filtration is a very interesting process. The actual design of a depth filter is quite complicated, and from a chemistry perspective, there's a lot of work that can be done to optimize the design, not just to remove cells and cell debris, but also to remove some of these contaminants. So depth filters used primarily to in the production of biotherapy. I should say this. Depth filters also used to remove impurities from bacterial cells. So one thing I hadn't stressed so far, because we're not talking so much about cell culture, is what sort of cell line should we use, right? So you could use E. coli, right? E. coli, you can use bacterial cells. You could use, we've been talking about mammalian cells. Mammalian cells, typically people use CHO cells, Chinese hamster ovary cells, or murine hybriderma cells, so various mice cells that are cancer cells. But there's interest in insect cells, plant cells, all sorts of cells, right? One thing about all these cells is they're so-called immortalized cells. So these CHO cells have been taken from Chinese hamsters at some point a long time ago, and they've been modified so that now they can grow forever. Okay? So cancer cells grow forever. That's why they end up killing you, because they just grow out of control. Most cells stop growing. There are regulatory methods and mechanisms that stop them from growing. But these are immortalized cells. The way you choose a cell depends on how complicated the protein is you want to make. So bacterial cells don't have the machinery to make very complicated proteins like mammalian cells. So it really depends on what you're trying to make. But if you can use bacterial cells, it's better because they are much easier to grow. They grow much faster. They're much less expensive to grow. The growth medium doesn't need to be so complicated. So it depends on what you can do. Okay? But if you're growing bacterial cells, the problem is here. Initial cell recovery is typically by centrifugation or tangential flow filtration with washed cells that are then lysed. Because in the case of bacterial cells, the product is typically precipitated inside the cells. So you have the lysed cells. Mammalian cells are nice because I told you they can excrete the protein of interest. Okay? So if you do that, then typically you take the cells, you centrifuge to spin them down, right? Wash them means that you change the buffer into something that you like, and then you have to lyse them. But once you lyse them, that's really very complicated because, and sometimes you have to do it, but then it's complicated because you've got a huge mass of very tiny particulate matter, enzymes, all sorts of things that are very difficult to remove. And so this particular device, this M-phase, which is an anion exchange depth filter from 3M, and it's a relatively new product, can produce up to 3 log removal of DNA, 7 log of endotoxin with a small reduction of host cell protein, reducing the rate of fouling on subsequent cation exchange chromatography columns. So again, there's a great deal of interest in using these sort of devices where you can remove these contaminants that would affect further downstream purification. Okay? Then diatomaceous earth-containing depth filters are effective at removing precipitate molecular antibodies after a low pH hold and virus inactivation step. So again, if you look at that scheme I showed you, there's that low pH hold I talked about, right? So I told you that will work as long as you don't affect your protein. But one thing that's very important that I'll keep coming back to, all of these unit operations have some effect on your protein. So actually, Professor Jacob just told me, some of you may be confused about monoclonal antibodies. So monoclonal antibody is a protein. Just think of it as a protein, okay? A complicated protein. The point is this. Proteins are very easily damaged, if you like. And these are small changes in conformation. But small changes in conformation are not good because A, it might reduce the therapeutic effect. But more importantly, it can cause aggregation. It can cause them to adsorb on columns because you get hydrophobic residues exposed and so forth. So you want to remove any sort of aggregates that you form. And so those sterile filters, or in this case, if you use a depth filter after a low pH hold step, you would remove any of the protein that you damage. Okay? So that's another important point. Depth filtration is inherently a batch operation. I just said that. That makes sense, right? You run it through there, you adsorb your foulants. After you adsorb your foulants, if you want to reuse it again, you've got to get rid of all these foulants. Then you've got to validate that you have got rid of them. And that is exceedingly difficult to do. How do you validate that you've removed all the virus particles or all the endotoxin? It's impossible, okay? So they're inherently single use, and then they're discarded. Dead-end filtration skid for continuous biomanufacturing, in which the feed is switched between parallel depth filters at previously set endpoints for the maximum turbidity or pressure demonstrated for initial clarification of recombinant proteins produced by E. coli has been actually demonstrated. So they're single use, but I told you we are moving, or we'd like to move towards continuous biomanufacturing. Continuous, remember, in the biotech industry means maybe running for 1 month, maybe running for 2 months maximum. But that's a pretty long time, okay? Because currently it's all batch process. You grow one batch of cells, takes about maybe a week if it's a mammalian cell to get to your product, and then you stop. So if you're going to run this continuously, you have a completely different validation problem, because before I told you, you want to run and everything and finish it in one shift. In a batch process, every operation is done in one shift, okay? Except, of course, cell culture, because you've got to wait till the cells grow. However, if you're going to do continuous biomanufacturing, this idea of one shift disappears. So speed is not that important anymore, right? Because you're going to run for 2 months or 1 month. So it doesn't matter that you have to do it quickly. What you want to do is to make sure that this has the capacity to keep going. So now you can run at lower fluxes, but it needs to keep operating, right? You can't stop. And so with depth filters, that is a problem because they'll have a certain capacity. They'll absorb, and at some point, that's it. So if you can have parallel rows of these, you can keep switching from one to the next because you can't break the process. If you do, it'll get infected, right? It's got to be totally sealed all the time. But the question comes up then, if you are trying to switch from one row to the next, at what point do you do that? How do you have in a manufacturing process a protocol for at this point I switch over and I can guarantee that I got the capacity, I got the removal I had before? That's a major issue. So you can do it based on endpoints. The turbidity goes up in your product. You can do it by looking at pressure and so forth. Another problem too, if you're running through, say, so stream A and you're waiting for the turbidity to increase and then you go to stream B, then there's be a variation in your product, right? Because the turbidity is increasing. You don't want that again. So a major issue these days in continuous biomanufacturing is how you set these set points, okay? So general approach could also be used to adapt other normal flow filtration to continuous biomanufacturing. Sterile filtration, virus filtration, also dead end, they're all normal flow filtration. Again, the big problem is how can you work out when to switch from one to the other? So that's a major challenge these days in industry. So these are some examples of the depth filters. The left-hand figure shows you whole banks of them and how they are run. The right-hand one here is a millipore depth filter cartridge with 2 depth filters of different grades, and you can see them here. They are cut apart. And the final layer of cellulose acetate is a pre-filter. Also, yeah, you should consider it like this. When you have multiple grades of depth filter in one unit, the level above the next one actually acts as a pre-filter for the next, one, okay? Large-scale microfiltration systems for harvest of recombinant DNA is shown on the left for Chinese hamster ovary cells. The first one is a micron 0.2 micron polypropylene hollow fiber microfiltration system with 174 square meters of membrane surface area. That's this first one. And the second one is a millipore ProStack flat sheet membrane system, 186 meters squared, and it's 0.65 micron pore size, hydrophilic PVDF. Okay. So getting back to our figure here, I've talked a little bit about this depth filtration, and actually I should have switched never mind, I'll switch the pointer for tomorrow. So depth filtration comes here just before we move into the capture step. Okay. So now the theory of depth filtration, I think Professor Jacob talked a little bit about it. So maybe I'll go into a little bit more detail, and then that will add to some of the stuff that he talked about. But dead end or normal flow filtration occurs frequently in the biotech industry, and it's also used in sterile filtration and virus filtration. So normal filtration may be run under constant pressure or constant flux, and he actually showed you some equations. If you are in that area, that you would have noticed some were constant pressure, some were constant flux. What do I mean by that? So you know a depth filter, right? I've shown you a depth filter. You have everything comes in, everything is retained. The flow outside is just the product. I can run this so that I apply a certain pressure driving force at the top, and that's a constant pressure. So if I run at constant pressure, what happens? Eventually, the filter starts to plug, right? You're removing more and more stuff. So as the filter plugs, my pressure is the same, but if you look at this equation here, we define the flux. So everybody knew what flux was, I hope, right? So flux is the volumetric flow rate divided by area in this case, which can also be written here mathematically as 1 on the area multiplied by the derivative of volume with respect to time. So this flux is going to be given by this equation here. This is called Darcy's law, where the driving force is the pressure drop between what I apply, and the bottom term is just a resistance term. Okay, if you are aware of this area, there are 2 resistances we talk about. We talk about the, I think I'm going to just do it here, the membrane resistance and the cake resistance. Okay, so the cake resistance is what's starting to adsorb there, and this is changing with time. So if this resistance is increasing with time and the pressure drop is constant, what's going to happen? the flux will decrease with time. And eventually it will go to 0, but we never run to 0. We stop well before that because that's not practical. That is called constant pressure operation. Another way to do it is for me to let the pressure vary. I can keep increasing the pressure, ensuring I have a constant flux all the time. That's called constant flux operation. Okay? So it can be run in either way, constant pressure or constant flux, depending on the operation. If we consider constant pressure first, and I'll probably stop at constant pressure for today. So it's described in terms of 4 blocking models, which we saw earlier: standard blocking, complete blocking, intermediate blocking, and cake filtration. I'll explain those in a minute. All flow blocking models are based on this equation. So if you haven't seen this equation before, if you're not in chemical engineering, that's okay. Just think of it as the flux. What I'm trying to recover is going to be a driving force divided by some sort of resistance. Okay? By the way, mu here is the viscosity of your feed stream. Mu is important because the viscosity changes a lot, especially as you start to get higher protein concentrations. So I explained the terms below this. Okay? Permeate flux for clean membranes, that's this, how I calculate this membrane resistance term, is given by something called the Hagen-Poiseuille equation. Again, if you're studied fluid mechanics, you'd know what that is. That's for laminar flow in tubes. But it's just an equation that determines the flow rate as a function of pressure drop, okay, in tubes. All right, so if we look at the theory, we can say that the flux is equal to, for clean membranes, is given by the following based on this Hagen-Poiseuille equation. All you need to know is for a clean membrane, in other words, I'm running water through this membrane, the flux, what I want is the flow rate divided by the area, which depends on all of these terms here. You can see there's the pressure driving force, the pressure I'm applying, plus this Rm term, which has grouped together a whole lot of variables here. That is my resistance to flow. Okay? If you want to know what the actual variables are, mu is the viscosity, A is the membrane surface area, L is the length of this, the depth, and then we have N, which is the number of pores, and D is the diameter of these pores. If you're not familiar with that, don't worry about it. It's just that the driving force divided by a resistance. Okay? Now, so there are these various blocking models. So the blocking models, really what we can say is this. If I have a pore and stuff flowing through it, I could say that some of these foulants adsorb onto the walls of the pore, right? As they absorb onto the walls of the pore, they constrict the pore. So that's called that's one type of blocking. Okay. So if we look at standard blocking, we can also get fouling occurring on the outside at the entrance to the pore. So standard blocking model assumes that the solid absorbs onto the pore walls. The other 3 blocking models assume fouling occurs on the external surface. So there's 1 for the walls, 3 for the external surface. We can have complete and intermediate blocking, describe a reduction in the number of pores available for permeate flow due to blocking by the solute. And all flow blocking models assume that the resistance to filtrate flow increases with increasing filtrate volume. That's important. The resistance increases as you filter more material. Why? Because there's particulate matter in the material, so you're removing more and more of the particulate matter. So that's very important. The resistance increases the more you process. Okay? And so we can then come up with these equations. Somebody called Hermia defined the resistance coefficient. Mathematically, it's given by this, but it's just a mathematical derivation that shows that all of these blocking models come from that Darcy's equation and Hagen-Poiseuille equation. So perhaps the important things are this. The blocking models make a few assumptions, and this is where we have to be careful. It's assumed that you have straight pores. So they're not tortuous pores, right? But unfortunately, membranes have tortuous pores, if you look at, except for track-etched membranes, they have tortuous pores. Secondly, the blocking models actually are assuming a uniform diameter, but except for track-etched membranes, you have all sorts of diameters, right? So that's not exactly true as well. And so like this, there are quite a few, and you assume laminar flow. So there are quite a few assumptions, which is why actually the blocking models sometimes don't work that well, okay? Now, what I have here is rather small because I didn't want to go through all the details, but one can write these standard blocking models in terms of these rather simple equations, and what you end up with is Q on Q naught, your flow rates, is given by here as a function of time with this parameter beta. So you can plot these, you can linearize them and plot them, and from that you can get your values of that imperative, that constant beta, okay? And that beta constant is interesting because there are various values you can get for that, and those values tell you what sort of blocking you have. Is it standard blocking, complete blocking, cake filtration, so forth. So that's what these details are about, okay? So if all of you were engineering students, we could go into that in more detail, but I think at this stage we will just skip that, and if you're interested, you can see me tomorrow or sometime and we can talk about it more. So I think I'm going to stop with it's almost 4 o'clock. I'll stop with this slide, I think. So the blocking models can be done both for constant pressure and for constant flux. Okay? So depending on what mode you have, these blocking models are kind of interesting. If it's constant pressure, you can put on your y-axis Q versus Q naught. Your x-axis can be time. You do a log linear plot, and you'll get your value of beta coming out of it. Here's, you can do it for intermediate, for, so basically you have your data, and you plot it this way, and you come up with your value of beta. And as I say here, where beta are constants, and actually, if the value of beta is 2, 1.5, 1, or 0, you have complete standard intermediate blocking or cake filtration. Okay? So if it's a value of 2, if it's a value of 0, sorry, you have complete blocking. So the particles come and block the pores directly. If you have a value of 1.5, you have a standard. If you have a value of 1, you have intermediate. You have basically adsorption on the pore wall. So in this way, you can tell what's happening. Okay? That's interesting, except there's a problem, because as I told you, that assumes you have straight through pores. And the problem is that often you get values of 1.5 or 1.67 or 2.1 or some odd number. Okay? So then what do? Do you say I just round up to the nearest one, or what do you do? That's one problem that occurs. The second problem is actually, if you look at this equation, you've got the second derivative here, right, of time with respect to volume. If you take experimental data and try to get these derivatives, any small error is multiplied a lot. So again, is the fact you got 2.1 or 1.8 due to experimental error, or is that really real, you see? So this turns out to be quite a problem. So I think I'm just going to talk about the limitations and stop. So often a transition from one type of fouling to another is seen, especially pore constriction to pore blockage to cake filtration after processing large volumes of filtrate. So you don't get a straight line, you get something that's curving, which actually kind of makes sense, right? Because you can change from one regime to the next as you keep running these. Another problem is something called lateral permeability. So for track H membranes, you have straight through pores. So if you block the pore, you blocked it forever, right? But in actual membranes that you may cast, you have links between the pores, right? So you may have blocked this one at the entrance, but stuff can come from the side and go through. In fact, you want to have lateral permeability. It increases the capacity of the membrane. But that doesn't agree with the blocking models, and that explains why sometimes you get these odd numbers, and sometimes higher than 2 even. And there are papers that have been published on this. So that's what I say here. Assumption of uniform non-connected pores is appropriate for track H membranes, but not in the case of extended PTFE and phase inversion PVDF membranes. PVDF in this case has studied the effects of membrane morphology and the decrease in permeate flux on model proteins such as BSA and lysozyme, and use of blocking models to explain experimental data is sometimes difficult due to experimental errors. So the blocking models actually are a nice way to look at this, and interestingly, they are used a lot in industry. We'll learn when we come to virus filtration, that is how people size virus filtration membranes. It also explains why it is very difficult sometimes to come up with appropriate manufacturing processes because of inherent problems with these models and the assumptions one has made into them. So I think maybe that's a good place to stop. And then tomorrow, so we'll change the outline a little bit. I think tomorrow I'm supposed to talk about sterile filtration, but I actually have quite a lot to talk about here. So I'll continue with this, and then we'll move on to sterile filtration after that, okay? And that's probably also a good place because there's a bit more mathematics coming up in the next section, so we can break it up. Any questions? No questions? Yes?
You said you are going to use non-treating agents, right?
Yes. Yeah, typically I didn't talk much about it, but people use things like chitosan. You would have to use, where was it? Before this, right? Yeah, somewhere here. Turbidity here, right? It's a great filter. Here, precipitation or flocculation with chitosan or polymeric flocculants. Typically, though, people like to use things that are compatible and are not going, it is a very, you try to avoid adding anything new to the cell culture medium. So if you're going to use chitosan, that's fine. If you're going to use pH or some ionic strength, something like this, that's fine. Polymeric flocculants people do use sometimes, but you have to be very careful. If you use flocculants, say, from water treatment applications, the problem there is that if you're adding a cationic flocculant, it's not really prepared for biotherapeutic applications. So you often have a range of polymers there, and some of them may not be as benign. Okay, the monomers are often not very benign, so one has to be careful. But flocculation is something of great interest. Typically, though, people try to do it simply by adjusting pH or ionic strength.
We get a 4.7 log reduction in virus filtration using that filter?
You can, the newer ones are trying to show that. Yes, yes. So this that's M-phase, right? I think I mentioned. Yeah. So 3M just came out with that product, and they are quite keen to try and validate that. Again, of course, there's a problem because it depends very much on ionic strength and so forth. So again, validation has to occur on a case-by-case basis.
They are charged as well?
Yes, yes. They are charged. They have hydrophobic groups. It's a multimodal ligand that's put on the surface. Yes, yes. Actually, even virus filters these days have surface properties. Yes, yes, that are important. Actually, that's an interesting point. So, you know, I was going to talk about it more when I get to virus filtration. We have these number of different steps used for virus filtration, but regulatory authorities say they have to be what they call orthogonal, which means I can't say I had a virus filter, okay, a virus filter, and it removes, say, 3 log. So why don't I put 2 of those in series and say I've got 6 log? That will not pass. Because the argument is this, okay, so you remove 3 log, and presumably some viruses went through. But presumably your filter is such that those viruses are more likely to go through. So how do you know the next time you will get 3 log? It may be 1 log, it may be 0. So you have to use different mechanisms of action. Okay, so they do consider depth filtration and virus filtration, which is entirely size exclusion, to be different mechanisms of action. Depth filtration is using surface properties. So that's an important point. Yes, yes. Any other questions? Okay, thank you. So we'll see you tomorrow.